All right. Hello, everybody. Welcome to the thesis defense, to the dissertation defense of Alphonsus Adu-Bredu. Alphonsus came to us in 2000 in the height of the pandemic and will be graduating in I will say is expected to graduate in record time. We got one more hurdle here. And after lots of time in the lab and a lot of Buffalo Wild Wings, has gotten to this point where he's ready to defend. He's been doing great work in terms of in terms of task and motion planning for bipedal robots, bipedal humanoid robots, especially for the agility robotics digit, and is right now finishing out an internship at Boston Dynamics, which I believe he'll continue at in the future. So with that, I will pass the. I also have to say, I appreciate everybody spending time. I know this is the height of vacation time. I'm taking time from my vacation for this. So I just wanted to thank everybody for coming out. I think we've got pretty good attendance given that it is what is it, July 31st. And so with that, I will give the floor to Alphonsus. Please start.
Thank you, Chuck. All right. Welcome everyone to my PhD thesis defense on long horizon planning under uncertainty and geometric constraints for mobile manipulation by autonomous humanoid robots. And we're gonna get started. Yeah, so our daily lives are filled with long horizon tasks such as cooking, doing dishes, cleaning the kitchen, and etc. That are, to be honest, quite tedious to do. And for some other people, it's actually impossible for them to do it because of various physical impairments. And so as a roboticist, I often think about how to replace, how to get robots to basically do some of the tedious tasks that humans do not really like to do. And so during my PhD, I've been thinking of this main question: how do we equip humanoid robots with the ability to perform long horizon tasks? And in summary, how do we replace the Alphonsus with the digits and get it to do all of the kitchen tasks we want it to do, clean our kitchen, cook meals, etc. And you might be wondering, is this actually possible? Do we have humanoid robots that are capable of doing this? And I would say, yes, we actually do. And so you can see from these cascades of videos of the humanoid robots digits doing some really cool manipulation and mobile manipulation tasks, like picking up a package from a bin, packing groceries into a container, transporting cookie boxes from one place to the other, lifting boxes of unknown masses, transporting boxes, and even playing cornhole. And all of these videos are not like high production videos. All of these videos were basically from experiments that were performed like right here in the robotics department here, mainly downstairs in the biped lab. And so we certainly have the hardware and even the mature control systems to get humanoid robots to perform all of the domestic tasks we willing to perform. And so what is still holding them back? Why don't we all have digits in our homes doing our chores for us? And so to answer that question, let's look at the domestic tasks in much more detail. So one domestic task we probably want digits to do is to do our dishes for us. And it's quite difficult to actually get a robot to do dishes, mainly because all of the dishes or the objects it needs to manipulate are all often in a clutter. And so there's going to be a difficult perception problem in actually like detecting all of the objects of interest and figuring out ways to like, estimate their poses, because in clutter, the perception is going to be hard because there's going to be occlusion, poor lighting conditions, and you can even have atmospheric objects like translucent objects and transparent objects. Another difficulty digits might face is basically how to decide how to satisfy certain physical and geometric constraints. For example, how low should digits squats to reach the bottom shelf, or how high should digits stretch to reach the top cabinet? All of these are physical constraints or geometric constraints that robots like digits would have to satisfy in order to be able to pack the dishes after washing them. And thirdly, digits would also have to be able to plan under conditions of uncertainty. And so here, I'm trying to figure out where the white plate is because I'm done with my scrambled eggs. I thought it was in the middle drawer. I opened it, I couldn't find it. I updated my belief and later found it in the bottom drawer. And I am the only one who uses this kitchen. I live in a one-bedroom apartment. And even still, I often forget where I place my plates or my cooking utensils, etc. And so if I'm even forgetting where I place my objects, how much more a robot like digits? If digits is like living with us in our homes, digits would have to be able to figure out exactly where all the locations of objects are. So there's going to be some uncertainty in the locations of objects. There's also going to be uncertainty in the estimation of the poses of objects, like getting the right pose of objects before it can actually manipulate these kinds of objects. And so we would need robots like digits to be able to plan for accounting for all of these kinds of uncertainties. And so in summary, the three main difficulties I pointed out in the previous slides are difficulty in planning and low entropy object detection, difficulty in planning under uncertainty in object location and state estimation, as well as being able to plan optimally under geometric constraints. And so all of these different kinds of problems could be summarized into this simple thesis question. How should autonomous humanoid robots plan for long horizon tasks while accounting for uncertainties and geometric constraints that exist in the real world environments? And so this is the central thesis question that my various works hope to address. So these three main difficulties basically sum up to the three main contributions of this thesis. So the first contribution is a robot planning approach under uncertainty and a low entropy object detection. And the second contribution is going to be robot planning under uncertainty in object location and state estimation. And then finally, optimal robot planning under physical and geometric constraints. All right, so let's move on to the first contribution, which is robot planning under low entropy object detection. And this work was published in the Robotics and Automation Journal in 2021. All right, so let's go back to my kitchen. Our goal is to enable robots to efficiently plan for tasks in cluttered scenes, such as doing dishes or packing groceries. And as I mentioned earlier, these situations often pose very difficult perception problems, mainly perception in these adversarial conditions. However, over the past 10 years or so, there have been some really great advancements in perception systems. So modern perception systems are able to estimate the state of objects in clutter with very high accuracy or very low entropy. And some examples of these kinds of works are as follows. And so given the capability of modern perception systems to estimate objects with very high accuracy or low entropy, how then do we exploit these estimations in order to speed up our planning process? How do we exploit these low entropy situations to get robots to plan more efficiently? And so in this work, we propose lay sample as an approach for robots to perform task planning on low entropy state estimates. And so what is lay sample and how does it work? And before we actually go into much detail, let's think of this two-dimensional spectrum. So we can think of robots planning algorithms on this two-dimensional spectrum, where the vertical axis represents computational tractability, which essentially means the speed at which algorithms can be run. And the horizontal axis represents the assumed uncertainty of the state space. That's how much uncertainty does these planning algorithms assume over the state space. So on the far left of the spectrum, we could think of classical planning approaches. So classical planning approaches are approaches that assume there is no uncertainty in the state space. So they assume that the state space is fully observable and the robot knows exactly where all the objects of interest are, and the effects of the robot's actions are deterministic. So there's no uncertainty in the effects of the robot actions. And so these approaches end up being very fast to compute. And so they end up being like really fast to compute online. And so they end up being really computationally tractable. However, because they don't assume any uncertainty in the state space, if they are deployed in an environment where there's a bit of uncertainty, they often fail. And on the far right of the spectrum, we have belief space planning approaches. So belief space planning approaches assume there is really high uncertainty in the state space. And so because of that, they basically perform very explicit probabilistic modeling of the state space before they make any single action. And so they end up being quite inefficient to run in real time. However, as I mentioned earlier, modern perception systems are pretty good at giving us high accuracy state estimates of the world. And so in order to exploit them, we need algorithms that fall in this sweet spot in the middle, which are low entropy planning algorithms that are able to exploit these high accuracy, low entropy state estimates of these modern perception systems. And that's the region where lay sample fails. So what is lay sample and how does it work? So lay sample stands for low entropy sampling planner. And this is how it works. So we have our digits robots here. And so given some RGB observation from the digits robots, we first employ a state-of-the-art object detection approach, like say a mass RCNN, to detect the objects of interest. And the object detection approach basically draws a bounding box around each of the objects of interest, and then also returns some discrete probability distribution of the potential identities of each of the objects. So for instance, the the object that is bounded by the light blue box has like a 35% probability of being a mag or a 25% probability of being a gel. So given these estimates, we build a belief scheme graph, which is basically a geometric representation of the inter-object geometric relationships. And so an on relationship between two objects basically means object A is on object B, and a beside relationship basically means object A is beside object B. Given this belief scheme graph, we basically sample a deterministic scene graph from that, formulate that as a symbolic planning problem, and plan a sequence of symbolic actions. Next, we ground these symbolic actions to get continuous parameters and then pass that to the whole body controller of the robots. And then the robots then executes each of the actions in turn. So after the execution of each action, it performs a validation routine. And this validation routine basically checks whether the observed effects of the action matches the expected effects of the action. So if the action was to pick up a pair, the expected effect is that after the action is executed, the robot has a pair in hand. And the observed effect is basically check whether the robot has a pair in hand. And so if these two match, then we are successful, and then we move on to the next action and execute it. But then if there is an inconsistency between the observed effects and the expected effects, we call that a mistake. And when there is a mistake, we basically re-observe the new world, reinitialize our beliefs, and then repeat the whole Scheik-Weber cycle. And so we demonstrate Scheik-Weber on a simple grocery packing scenario in simulation. And in this task, the task is basically to pack grocery items into a container such that certain constraints are satisfied. And here the constraints are basically that the light items will go on top of the heavy items in the grocery bag. And so we are going to see, and so in this simulation, we basically compare this sample with classical planning and belief space planning approaches. And I'll talk about each of them in turn. And so we start running the algorithms on each of them. And so let's talk about a mistake. So a mistake, as I said earlier, occurs when the observed effect of an action doesn't coincide with the expected effects of the action. So here, the robot expected to pick a tennis ball, but it ended up picking a pair because of perception errors. And so once this happens, the robot reobserves the ball and repeats the whole Scheik-Weber cycle. And so this is what we count as a mistake in the whole routine. So it continues to perform the grocery packing based on the actions that are planned from this algorithm until it's done. And so now let's do some qualitative comparison between the sample and the approaches. So the first approach is FF replan. So FF replan is a classical planning approach, and it doesn't account for any of the uncertainty in the state space. It assumes there is no uncertainty in the state space. And as a result, it ends up making much more mistakes than the lay sample, which accounts for the entire uncertainty in the state space. And so this sample ends up being more robust to perception errors than FF replan, which ends up resulting in much fewer mistakes and faster task completion for lay sample. Next, let's look at BP stream. So BP stream is a low entropy planning approach. However, it's replans after every action. Because it replans after every action, it performs much more plans than is actually necessary to accomplish the task. So it ends up taking longer than lay sample to complete the task. And then next, we'll look at the belief space planning approaches. So PUMCP is a belief space planning approach, and how it works is it uses a multi-colored tree search to plan on a belief of the scene estimates, whereas lay sample uses a regular symbolic planner, which uses an A-star algorithm to plan on this belief. And because of this, lay sample ends up planning more efficiently and completes the task much faster than PUMCP. And then finally, despots. So despots is also a belief space planning approach. However, it's basically an advancement of PUMCP in that it performs tree search on a much faster lead tree than PUMCP. And this ends up reducing the time required for tree search, making despots much faster than PUMCP, but still slower than lay sample to complete the task. And so you realize here that lay sample, BP stream, and FF replan have finished their grocery packing, whereas despots and PUMCP are still waiting to finish. And so despots finishes fourth, and then PUMCP finishes last. All right, so let's look at some quantitative experimental results. And so we performed a bunch of quantitative experimental results, but in this talk, I'll talk about just two of them. And so the first result you're going to be talking about is the comparison of the planning and execution times of all of the algorithms. And so you realize from this plot that So the vertical axis basically is the duration in seconds, and the horizontal axis is each of the planning approaches. So realize from this plot that late sample plans much faster and can complete the tasks much quicker than the other classical planning and least based planning approaches. And so here the planning time is the cumulative planning time across the entire task. And then we also look at the comparison of the average number of mistakes. And you also realize that here FF3 plan, which is the classical planning approach that assumes there is no uncertainty in the state space, ends up committing much more mistakes than all of the other approaches, because all the other approaches account for uncertainty in the state space. And we also go ahead to basically deploy late sample on the physical digits robot and get it to pack some assorted items such that the light items go on top of the heavy items. And here we use the NEC RGB camera to basically capture perception data of the clutter of objects on the table. And we also fashion a manipulation system for digits, because digits doesn't come with a gripper. So we basically built this custom gripper manipulation system to get digits to actually pick up these assorted items and place them in a bin. Yeah, so digits is basically packing all of these into a bin, and and of course you could tell that we basically designed we basically chose objects that are good to that are basically go with the parallel plug grippers we had, because if we had chosen much more adversarial objects, it would have been very difficult to grasp. But yeah, we've been able to show that a late sample runs on a real world hardware and basically perform the grocery packing task. And so let's look at some summary and limitations of late sample. So in summary, we propose late sample as an approach for fast and efficient task planning under low entropy object detection scenarios. And in these scenarios, however, we were certain about the general locations of objects of interest. So for the grocery packing task, we knew that all of the objects we are interested in are all on the table. Or if we were to extend this to the dish washing task, we know that all of the objects we want to wash are all in the sink. And so we didn't have any uncertainties about where the objects are going to be. However, what if we do not know with certainty the locations of objects of interest? What if, and also what if there is an uncertainty in the pose estimation of the objects of interest, or uncertainty in the robot's own state estimates? How do we account for all of these kinds of uncertainties when performing planning? And so these questions lead us to the second contribution of this work, which is robust planning under uncertainty in object location and state estimation. And this work was published in the AROS at the AROS conference in 2021. All right, so an introduction of this problem. So long horizon tasks such as cooking are characterized by very large state and action spaces. And these large states and action spaces are often partially observable in reality. And so here, I'm looking for the white plates, but I thought it was in the middle drawer. I couldn't find it, so I updated my belief and later found it in the bottom drawer. So we would need to be able to get robots to perform these kinds of planning while accounting for all of these kinds of uncertainties in object locations, as well as uncertainties in the pose estimates of objects. So how do we get robots to plan long horizon tasks while accounting for the general partial observability that exists in real world environments? And so before we talk about our approach for tackling this problem, let's look at some related work. So the general class of approaches that address long horizon planning are called integrated task and motion planning approaches. And for integrated task and motion planning approaches, they can basically be classified under two main classes. So the first class are the sampling-based approaches. So the sampling-based task and motion planning approaches basically perform symbolic planning to get a sequence of symbolic actions, and then use certain sampling routines like motion planning sampling or graph sampling to get continuous parameters for these actions and execute them in turn. A more recent other class of approaches for task and motion planning are the optimization-based approaches. So these approaches basically formulate the entire task and motion planning problem as an optimization problem, and then solve the optimization problem to get their decision variables, which are basically the continuous parameters of the actions that are to be executed. And one core assumption these approaches assume is that the world is fully observable. So they assume that the robot knows exactly where all of the objects of interest are, and is able to estimate the poses of all of these objects of interest with 100% accuracy. But we know that this is not true. I think we live in the real world where the world is very partially observable. And there's no way to, it's not really reasonable to actually assume the robot has perfect information of the state space. And so more realistic approaches for task and motion planning are the partially observable task and motion planning approaches. And these approaches are able to account for uncertainty in mainly the estimation of objects of interest. And so this basically leads us to our contribution, which we call Shikrover. So our contribution, Shikrover, is basically an approach for long horizon planning that can account for arbitrary sources of uncertainty. And so some more introduction of Shikrover. So Shikrover stands for satisfying hybrid constraints with belief propagation. And Nikhil actually coined the name. So it's an approach for long horizon planning under uncertainty. So giving some high level goal and a prior belief, Shikrover first plans high level actions to accomplish the goal, and then probabilistically infers the continuous action parameters jointly, that updates its belief and replans whenever the actions fail to accomplish the desired effects. And so let's look at a brief graphical diagram of how Shikrover works. So given some prior belief space and some high level goals, Shikrover first generates a plan skeleton, which is basically sequence of actions, sequence of parameterized actions where the parameters are left to be filled later. So given this plan skeleton, we then first build a constraint network. So a constraint network is a factor graph, which is a bipartite graph made up of two kinds of nodes, the variable nodes, which are the circular nodes, and the factor nodes, which are the rectangular nodes. So we call the factor nodes also constraint nodes. So the variable nodes here represents the various continuous parameters needed in the actions of the plan skeleton. And the rectangular nodes basically represents the constraints that these continuous parameters are subject to. So for instance, if you had a continuous parameter, like say a joint configuration, the factor node that is connected to this joint configuration node would basically be a constraint like say joint limits, or if you had a variable node that is like a grasp pose, the factor node connected to it could be a grasp constraints, etc. And so given this constraint network, we do a couple of things. So we first initialize the observed variables in the constraint network with the prior belief of the robot, which is basically from the observation of the robot. And after initializing, we perform belief propagation on this factor graph for a number of iterations until convergence. And so after performing belief propagation to converge to some certain constraint satisfying values for these variable nodes, we then get a maximum likelihood estimates of these distributions in the variable nodes and then fill them into the parameters of the plan skeleton. So now we have a plan, a sequence of actions whose parameters are now filled out. So we can now then pass that sequence of actions to the whole body controller of the robots to execute them in turn. So after the execution of each action, we check whether the expected effects of the action matches the observed effects of the action. So if the action is to pick up a mag, we check whether the robot actually has the mag in hand after it's picked it, after that's executed the pick up mag action. And so if the robot is able to execute all of these actions in turn, we call it a success and we are done. However, if the robot is unable to execute, if there is an inconsistency because it basically tried to grasp the mag and missed it, that we then replan by first re-observing the wall and updating the belief, and then reinitialize the constraint network and repeats the whole Shikrover cycle. Or if necessary, we would basically generate a whole new plan skeleton and then repeat the whole cycle. And so let's see a more concrete implementation, a concrete example of Shikrover and on a kitchen task. So the task here is a contrite task of like cooking and serving a pair meal. And the uncertainty sources here are the uncertainty in the object pose estimation, as well as uncertainty in the robot's joint configuration estimation. All right, so here the task is to cook and serve a pair meal. And initially, the robot doesn't know exactly where the pair is. It knows it's in one of these three drawers in this drawer, in this cabinet, but it doesn't know exactly which of the drawers it is in. So initially, the belief of the location of the pair is uniformly distributed across these three drawers. So the robot just picks a drawer at random and searches. It can't find a pair, so it updates its belief and then opens a new drawer. This time it's able to find a pair. So it picks it up and then moves to the sink to wash the pair. Afterwards, it places the pair in the saucepan. Next, it wants to fill the saucepan with water. So it needs to grasp the mag first. But the first grasp failed mainly because of an observation error, an observation uncertainty. So the robot re-observes the wall and then repeats the whole Shikrover cycle to come up with a new sequence of actions. This time it's able to succeed at grasping the mag. It then moves to the sink, fills the mag with water. and then moves to the saucepan, pours the water in the saucepan, and then places back the mag, goes back to the stove and pushes a button to magically cook the pear. And then afterwards, it picks up the pear, places it on the tray, and then serves the pear to the table. And all of these actions were basically planned through the Shikara system. All right, so let's look at some quantitative experimental results. And so we basically compare the performance of Shikara with SS3 plan, which is also another partially observable task and motion planning approach that is only able to account for post-estimation uncertainty in the objects. And so in these graphs, we compare both algorithms on planning time in seconds as well as the number of errors. And you realize from the bottom graph, and the horizontal axis basically represents the various levels of uncertainty. So the sigma p represents the standard deviation of the Gaussian, represents the uncertainty in the object post-estimation, and sigma c is the standard deviation of the noise in the joint contribution estimation. And so you realize that because Shikara is able to account for arbitrary source of uncertainty, is able to account for both object post-estimation and joint configuration estimation uncertainty. And so it ends up making much less errors than the other approach, which is SS3 plan. And that corresponds to Shikara taking much less planning time, much less cumulative planning time compared to SS3 plan, because if you make a mistake, you'd have to actually replan and replan and replan. So the more times you replan, the higher your accumulated planning time ends up being. Yeah, and so Shikara has much better performance than SS3 plan in these regards. So let's look at some summary and limitations of Shikara. So in this work, we proposed Shikara as an approach for long horizon planning under object detection and state estimation uncertainty. And Shikara employs non-parametric leaf propagation to satisfy implicit geometric and physical task constraints. However, the number of particles and the number of iterations needed to get some convergence in the leaf propagation approach actually increases with the complexity of the task constraints. And so what if we want to satisfy more geometrically complex task constraints? So for instance, since we are dealing with a humanoid, what if we have like constraints on the full kinematics of the robots, which the kinematic is also very high dimensional. So what if we have constraints on that? That would mean that we'd have to generate a much larger number of particles. And this would also result in requiring much more number of iterations. And this ends up being computationally infeasible for running in real time. And so we would need a more explicit way of accounting for constraints. And also, what if we want to guarantee some level of optimality of our plans? What if we want to optimize our plans to minimize the time spent or energy usage? How do we get our long horizon planning approaches to be able to do all of these things? And so these questions lead us to our third contribution, which is optimal robot planning under fiscal and geometric constraints. And this work was published at the ARIOS conference in 2022, last year. All right, so I swear this is the final Alphonsus video. All right, so we want to plan actions for long horizon tasks that requires the satisfaction of certain fiscal constraints, like how low should I squat to reach the bottom shelf, or how high should I stretch to reach the top shelf, or how should I be able to perform all of these tasks while satisfying the constraints of, say, static balance, where my center of mass should always be in my support polygon, or some other complex kinematic constraints. How do I generate a plan that is able to satisfy all of these complex geometric constraints? And also, I would also want to optimize for, I also want my plan to optimize for certain quantities like energy usage or time spent, because humanoid robots have a lot of very powerful actuators. So digits, for instance, has a number of actuators, and I think 20, and these require a lot of energy. And so you wouldn't want them to be executing suboptimal plans that end up like taking a lot of time and using up all the energy budgets for performing a task. And so we want to be able to compute plans that are energy efficient as well as take much less time. So how do we formulate all of these in a single plan problem and get optimal plans that are optimal to the kinds of quantities we are interested in? And so to answer these questions and introduce our approach, let's look at some related work in this field. So symbolic task planners have existed since the 50s, actually, and they plan purely in the symbolic abstract domain. And there have been some really cool approaches for symbolic planning, like fast downward, fast forward, hyperplan, etc. And these approaches are very fast, and they, as you know, uncertainty, and they also plan in a purely symbolic domain. They don't have any notion of real numbers or have no notion of like optimizing for any real quantities. And so because of that, they can't be executed on their own on a physical robot. In order to actually execute a symbolic plan, they have to come up with a way of grounding them. And so this leads us to sampling-based motion long horizon planning. So sampling-based long horizon planning basically does exactly this. So generates a symbolic plan, and then it uses sampling-based routines like grasp sampling or motion planning sampling to generate continuous parameters for these symbolic actions, and which are then now executed, which can then now be executed in the robots. And sampling-based motion planning often don't have any notion of optimality. They're only trying to satisfy certain constraints. So it's just a satisfiability problem, not an optimization problem. And another drawback of sampling-based approaches is you can only specify symbolic goals. You can't really specify a sampling-based task and motion planning algorithm to optimize for a specific quantity like energy usage or whatever. It's going to be very difficult to do that. They're not really designed for that. They're only made to satisfy symbolic goals. And so we need a much more general task and motion planning approach, a long horizon planning approach. And this leads to the birth of the optimization-based long horizon planning approaches. And so one of the first of its kind was logic geometric programming. And this approach basically employs Monte Carlo tree search for symbolic planning. And it then uses this symbolic plan to enforce feasibility in a nonlinear constraint optimization for continuous parameters. However, how this works is it has a very stratified approach where it first performs the symbolic planning and then uses those symbolic actions to basically enforce constraint. It doesn't actually solve both of them simultaneously. And so you could end up with situations where you get a perfectly logically feasible symbolic plan that is not geometrically feasible because there was no communication between the two when the plan was actually being output. And so we want to have a planning approach that is able to jointly optimize for both symbolic actions as well as their continuous parameters in a joint optimization problem. And so that's where GTP MIP, a proposed approach, comes in. I mean, that's the main strength of GTP MIP. And so how does it work actually? So GTP MIP actually stands for Grounded Task Planning as Mixed Integer Programming. And so we propose GTP MIP as an approach for optimal constraint long horizon planning. So given a task with symbolic and continuous goals and constraints, GTP MIP is able to output a grounded plan made up of logically consistent actions, each with optimal continuous parameter values. And these actions can then now be passed to some whole body controller of the humanoid robots to execute in turn, because they all have like optimal parameters. All right, so how does GTP MIP work? So we first described the grounded task planning problem in a special language which we developed for this work called the hybrid PDDL description. So this is basically an extension of PDDL to allow it to have continuous preconditions as well as continuous effects and action dynamics as well. So this way we are able to describe grounded task planning problems which allow us to optimize for both the discrete actions as well as their continuous parameters. So given this HPD description, we then pass that into a hybrid panel graph, which is a compact representation of the plan space. And it's made up of alternating layers of state levels and action levels. And each state level has both symbolic states of fluence as well as continuous constraints. And so given this hybrid panel graph, the next thing we do is we come up with a way of encoding this planning problem as well as the task objective and task goals into a mixed integer convex program. And these three components are the main contribution of this work. And so once you have the mixed integer convex program, the next thing to do is to solve it. And we don't need to write a solver because the operations research people have done a lot of really good work in coming up with very fast and efficient solvers for optimization problems. And so we use an off-the-shelf solver, in this case, Groby, because Groby is the fastest out there. Even though it's commercial, I think it has a student license, and so anyone can use it. And so we use this solver to solve this mixed integer program to get an action sequence. So this action sequence is a grounded action sequence. So each of the symbolic actions are output from the solver, and the continuous parameters are the optimal continuous parameters with respect to the specific objective function we specified in our mixed integer program. We can then pass these grounded actions to the whole body controllers of our robot stages, in this case, to execute. And so I talked a lot about mixed integer program. So what exactly is a mixed integer program? So a mixed integer program is essentially an optimization problem. And so has all the various components of an optimization problem. It has an objective function. So objective function is basically a function that returns a scalar value, and we usually want to minimize the scalar value. And so this function could be a function of basically the decision variables of our problem, which basically measures like how much energy is spent in this environment or in this plan, or how much time we spend. And so it returns a scalar value, and our goal is basically minimize the scalar value. So that's the objective function. And it's also subject to certain equality or inequality constraints. And these constraints could be task constraints like stance pools with respect to the object, or grasp pools with respect to the object, or whatever have you. So this could be either equality or inequality constraints, or even joint limits. But the peculiar thing about mixed engineering programming compared to other optimization problems is that it allows you to generally optimize for both integer and real decision variables. And so this is the key feature of mixed engineering program that makes it good for task and motion planning, because it allows you to optimize for both the symbolic actions, which we could represent with integer values, as well as the continuous parameters, which we could represent by real numbered vectors. And so this quality of being able to optimize jointly for these symbolic and continuous parameters allows us to basically formulate our entire task and motion planning problem as mixed integer programs, which we can solve to outputs grounded plans, which we can then pass to whole body controllers to execute. And so this is basically a brief description of how they can work pretty good. I could go into details if there are any questions, but I just got time. I'm just going to move forward. All right, so let's look at some experiments. So our first experiment is we basically compare the symbolic planning capabilities of GTP-MIP with the off-the-shelf symbolic planning approaches, and on a number of problems. So all the numbers in this table are basically time in seconds, and the problems here increase with difficulty. And so problem 1 is the easiest problem, and problem 5 is the most difficult problem. And difficulty basically represents the number of objects in this symbolic planning problem. And so you realize that for small to medium-sized problems, that's problems 1 to 3, the solve times of GTP-MIP is actually quite competitive with those of the other pure symbolic planning approaches. However, once the problem starts to get quite large in problems 4 and 5, you realize that GTP-MIP takes a lot more time than all the other symbolic planning approaches. And this is mainly because as the problem size increases, we have many more constraints, and with many more constraints, our solver takes much more time to actually solve it. And so depending on your specific use case, you may want to use just a pure symbolic planner and not GTP-MIP. But the benefit of GTP-MIP is you can solve for both, can optimize for both symbolic and continuous parameters. And so you can do both integer and low valued optimization. And so in some ways, we are much more versatile. And to basically show how versatile we are, we also get GTP-MIP to solve this 2D warehouse man's problem. So the warehouse man's problem is basically this. We want a robot to basically rearrange some boxes in a warehouse to fit certain geometric constraints. And so here we basically describe these geometric constraints in this table. And so this table has a bunch of numbers, a bunch of equations and inequalities, which represents the geometric constraints here. And so we formulate a GTP-MIP problem and then pass it to the GTP-MIP algorithm to solve, and it then outputs a sequence of actions, which are then executed by this 2D robot, which is basically a digits with a bird's eye view. And so the robot then executes the plans that are output from GTP-MIP, and we get it to, can you guess what it's spelling? Yeah, we get it to spell UMISH. And so it's able to, if you actually satisfy all of these constraints in the table, you end up spelling UMISH. And so this is a cool application. It shows that GTP-MIP can actually like optimize for these specific constraints and come up with this cool rearrangements. But these are all just 2D problems. So what shows your approach can work on 3D? And so to answer that question, we actually got GTP-MIP to work on a 3D problem. And so in this problem is a box rearrangement problem. And here the task is to basically get the full digits with the full kinematics and dynamics to rearrange these boxes into an inverted T shape. And the geometric constraints here are the constraints on the stance pose of the robot with respect to the object. So before you pick up an object, you should be in the stance pose with respect to the box. And it's also the center of mass position of the box, of the objects. as well as the constraints on end effector pools, so grasp constraints on the end effectors with respect to the objects to basically ensure that object is firmly grasped, as well as object placement constraints. So ensure that once you place an object on top of the other, the objects are like purely aligned so they don't fall off. And so we basically get GTPMIP to output a plan, and then pass this plan to a whole body controller, load whole body controller to execute this plan. So we get digits to basically lift these boxes and move them around. Yeah, and we are using here a full-fledged simulation environment. We're using Mojoko, and so it's physically realistic, and so the boxes will not probably align like perfectly, mainly because of like the robots. Once it was retracting its hand, it actually nudged the box a bit to the side, and so they might not perfectly align because of the physical realism of the simulator. But Digit gets the idea and rearranges the boxes in to basically gets this inverted T shape and satisfies all the constraints we subjected to. Yeah, so good job, Digits. And so you might be wondering, oh, this is a simulation environment. Like, can you actually get this to work on actual real life digits? And I'll say yes, we can actually get it to do that. And this is what we did. And so here, the task was basically to store a cookie box on the second pane of the shelf. And we had constraints on the robot stands as well as the stable grasp constraints. And we used the proprietary controllers on Digits to get this to work. And so here, Digits' task is to basically get this cookie box onto the second pane of the shelf. And so it first has to satisfy some stance constraints to actually be in the right position with respect to the table in order to pick up the box, and a grasp constraint to grasp it such that it doesn't actually fall from the gripper when it's walking. And then it has to place the cookie box on the second pane of the shelf. And so it basically aligns itself to the box, and it uses the April tag on the shelf to actually detect the shelf. And yeah, now it's the right position, so it places the cookie box on the second pane of the shelf. Yeah, there's a lot of collisions because we are not actually doing collision avoidance. That's a lot more hard problem. So we're doing a bit of open loop here, but yeah, Digit gets the idea and is able to execute the plan. And so what are some conclusions of this work and some observations? And so at the beginning of this talk, we talked about planning under low entropy object detection, how to get robots to plan under low entropy detection. And we came up with Lee sample to solve this kind of problem and get Digits to pack items into the bin. And we also went on to talk about planning under uncertainty in object location and state estimation. And we developed Shy Cobra to account for the uncertainty in the location as well as the pose estimation of the objects. And we also finally looked at how to plan optimally under geometric constraints. And we got Digits to pick up the Gersi box and then place it on the second pane of the shelf. And so, can we declare that we've solved all of robotics? No, there's still a lot more work to be done. And what are the kinds of work we need to do? So, some potential future work which could be extensions of the work presented in this thesis are as follows. And so, to get Digits to actually perform well in our homes, to actually get Digits to like come home and do stuff, we have a variety of different kinds of tasks we do in the home. And in this work, for each of the various tasks we got Digits to do, I as the operator, basically hand specify these kinds of constraints we want Digits to satisfy in, say, GTPMIP, as well as the task goals. However, this is not scalable. We cannot like assume that we know exactly how every home in the world is and how and the specific kinds of constraints we want Digits to perform to actually satisfy when we get things done in a home. And it's probably going to be difficult because there are so many activities or so many actions you could perform in a home, and you can't basically like enlist all of them sequentially. And so how do we come up with approaches for robots to basically infer task subgoals and constraints from human demonstrations? And we know that human demonstrations are like infinite online. There are lots of YouTube videos of people doing various home tasks, and probably just if you could basically get one video and basically run it through some routine that allows which is able to like infer the kinds of constraints that need to be satisfied, it would be, or if you come up with another approach for learning the kinds of constraints or figuring out the kinds of constraints and samples we need from human demonstrations. This would go a long way to allow us to basically program our robots without actually typing stuff, just program through demonstrations. And this is an interesting future which would certainly push us towards getting robots like digits in our homes to do our chores for us. All right, another kind of future work I think is certainly important to be solved in order to get digits in our homes is to figure out or infer or learn the right set of action parameters for a long horizon task. So action primitives for a long horizon task. And so in all of the tasks I described in this work, I basically unspecified all of the action primitives. So there was a pick primitive, there was a place primitive, there was a work primitive. And these are basic enough that I could just describe it using a few lines of code. However, there are much more complex action primitives like cutting potatoes or like pouring potatoes into a saucepan, which I have no idea to even how to even like begin to actually describe in code. Like, how do you actually describe like a process like this in code? How do you like specify pouring spices over potatoes or even stirring this? And this is like very difficult for humans to describe. And so how do we get robots to basically figure out or learn the right set of action primitives for a specific kind of task we give it to perform? And how do you even define what an action primitive is in this scenario? How do you get the robots to figure out the right action primitives for like cutting pieces of chicken and all that? This is a very difficult problem in many regards, both in terms of like the deformability of the objects that the robot is cutting, as well as friction and contact richness of the problem, etc. And so this is a very difficult problem, but this is the kind of problem we want robots to solve in order to actually get them to be useful in our homes. And so I think this is a really interesting feature work that needs to be explored. And finally, how do we include more object and environment dynamics constraints in solving for optimal task plans? And so I believe we've all seen this Boston Dynamics video of Atlas basically helping Brian, who's a construction worker on the scaffold, basically doing something. And in this video, the reason why it worked is because they basically gave Atlas very good inertia models or mass models of all of the objects it was interacting with. So they gave Atlas a good model of the plank, as well as Atlas a very good model of this heavy bag. And this allowed Atlas to basically solve in its MPC formation how to actually grab it such that it doesn't fall off and how to actually perform all of these actions. And one thing is all of these sequence of actions were scripted. So they didn't actually plan the right sequence of actions to perform. They just like sat down and figured out, came up with a script of like, do this, pick this up, and then go there and do this and do that. So all of this wasn't autonomous. They basically designed it just like a movie director would direct a movie. However, in order to get robots to be fully autonomous in the true sense, we want robots to figure out how to actually come up with these sequence of actions by itself, how to actually decide that, yes, I want to actually pick up this bag first before I pick up the plank of wood, and I have to squat this much because the object is very heavy, and if I don't squat this much, I'll not be able to get enough torque to actually lift it up. So all of these are things we'd want robots to figure out autonomously on its own. And one thing I've learned about the other summer is the more object information or model information you give to your algorithm, the better it's able to actually execute, is able to perform in real life. And so how do we give these dynamics information, not just on the low-level controller side, as in this video, but give this information actually on the task planning side, where the robot is able to reason about the mass and the inertias of objects when it's actually deciding these levels as these sequence of actions it needs to perform. And so how do we formulate such a task, and how do we formulate such a task and motion planning program to get this to actually work on the real world robot? Because we need to actually come up with a way of doing this if you're going to get robots to help us in construction or help us in kitchen or lift heavy loads for us. And so this is also a very interesting potential future work that would certainly move the field forward and get us closer to getting digits in our homes. All right, and now to some acknowledgements. I thank my thesis committee members, my advisor Chad, for first accepting me into the lab and teaching me what it means to be a good researcher as well as a good citizen of the robotics field. So thank you, Chad, a lot. And I thank Jesse, Professor Grizzle, and basically a lot of things. I mean, I learned a lot from GSI with you on Rob 101. Many some really new tricks, as well as learning a lot from your work ethic and how good you are at getting things done. I was amazed at like how fast you could get things done, and even as a 26-year-old guy, I didn't have as much energy as you did. Actually getting things done. I don't think I still do, even though I've started working out. But I'm very grateful. I had a good experience with you, and thank you a lot. And thanks to Nima. Nima has been a very good friend. And I think the first time I met Nima was at I was at MIT, but I don't think we ever talked at MIT. But first time I actually spoke with Nima was at the Logan Airport, Boston Logan Airport, when I was getting ready to come here for visit day. So he was the first professor I actually like had a conversation with, and all of these conversations throughout my time here at Michigan has been very eye-opening and inspiring. And thanks for all of your insights and wisdom into robotics. Thank you very much, and thanks to Professor Chai for all the time and effort he spends in giving me good critiques of my slides, as well as like helping me out and being very understanding with timing and everything. Thank you very much, and thanks to you, Professor Winfield, as well. I am very grateful for your calm demeanor and your great piano music on your YouTube account, and all the great things you've done. And thank you to my thesis committee members. None of this would have been possible without you. So thank you very much. And I'd also like to thank my lab mates. I learned a great deal from my lab mates, and I caught almost all my papers with Nikhil. And thank you very much for teaching me a lot about probabilistic inference and planning. And thanks to Grant for actually teaching me how to get robots to work and teaching me how to use digits. None of the work I've done in this thesis would have been possible without your help. So thank you very much. And thanks also to Digit 015. I mean, I've probably insulted you a lot of times, but thanks for being around. And thanks to Jesse for giving me the opportunity to use Digit, because I use Digit throughout all of my projects. And without digits, none of the works in this thesis would have been possible. So thanks a lot, Jesse, and I'm grateful. And of course, thanks to Professor Messner. So Professor Messner was my undergrad advisor, as you mentioned, and I learned a great deal from him. All I know in robotics is because of him. And the reason why I've been able to get stuff done quickly in grad school was mainly because of the help and experience all the stuff I learned from you as I did research with you in undergrad. That basically gave me a very good research foundation to build up on in grad school. So thank you very much, Professor Messner. Thanks for your brilliance, your kindness.
You're welcome. Great stuff.
Yeah, thank you very much. And thanks to my lab mates, thanks to Chad for taking us out and having a good time. And thanks for all the great times, all the Buffalo Wild Wings, as you mentioned. I definitely enjoyed a lot of them, and I probably gained weight because of that. And thanks to my friends here at Michigan Robotics. Thanks for all the great meetups we had at Grant's Place, all the good food and good barbecue. I enjoyed a lot of good meals there. Probably some of the best meals I ate, probably honorable. So thanks a lot. And thanks to all my friends here in the Robotics Institute. Like all the times we played soccer together, bantering about Chelsea and Man United. Those were like very good times that took out the stress of like doing research and made it easy to actually relax and then refocus on research. So thanks to everyone. Thanks to Mark and all my friends in the lab. And of course, thanks to my parents. I have a very large family, so 2 parents and 6 siblings, and a number of nephews as well. So they all have babies now. I think it's my turn now. But yeah, thanks to my parents. I don't know if any of them is online. No, I don't think any of them is on Zoom. But yeah, thanks to them for being such a good influence to me, and my mom for giving me all the food I needed to grow up into this handsome young man I am. Thank you very much. And thanks to everyone. Questions?
Let's thank Alphonsus for a great talk.
Oh yeah,
And as Professor Messner mentioned, I'll be joining Boston Dynamics in the fall to work on whole body control. So thanks to everyone. Yeah.